Floor is yours.
Thank you so much for the kind introduction. So let me share my screen. Oh, sorry, wrong slide. Right. Yes, you can see the slide, and well, I shall start then. So today we will talk about multi-scale simulations and how those can be used to foster materials discovery. Um, this talk is also part of dissemination activities for the EU project Open Model that I'm um, um, working on as a product manager. So I will talk more about what is it later and how it is connected to industry and how it enables or facilitates, as I said, the intake of computational models into the industry. And here, just a sneaky preview of what is a multi-scale simulation. So a bit of history to begin with. So back in the days, I would say in the 1980s, people started to really think about the role of molecular shape and molecular interactions in explaining the behavior, the observed behavior of soft matter. And that is particularly true for liquid crystals that have this rich behavior of phases where those particles that are kind of elongated rods can form these phases where they align parallel to each other. They can form layers, columns, so a very rich phase behavior. And interestingly, this behavior was captured, but with very relatively simple models. So in the first one that I'm citing here, they're just a two-dimensional lattice of rods. See, with the advance of time and with the availability of even of ever-increasing performant computers, people started to refine these models, and sure enough, we went from 2D to 3D, and eventually this Gay-Bern potential was developed that basically describes how ellipsoidal particles interact. And this work was done in Bologna, where I done my postdoc, and I kind of followed this line of research, started in Southampton with Jeffrey Lagarst and Claudio Zannoni, who was my supervisor in Bologna. Today, there are a number of coarse-grained models. So despite the fact that there are certainly very powerful machines out there, there's still an interest in developing those coarse-grained models where the matter is described with somehow simpler particles that account for two or more atoms. And I would say that one of the most cited and well-known is the Martini force field for biomolecular application. Somehow similar one is this ELBA model that also was developed in Southampton. And it also adds charges and dipoles on the beads. Then we have this MOLC model that I have developed while in Bologna, but that's not the end of the story. People still keep playing with coarse graining, and this is another example from 2 years ago. Meanwhile, there are a lot of activity in classic atomistic modeling. So there are, like here I cite two recent examples where a cell membrane interacting with nanoparticles was simulated, and the whole system is 1.5 million atoms. Or in the realm of electronic structure calculation, there are linear scaling DFT methods that currently can handle around 3,000 atoms in a single simulation. So that's quite impressive. But the real I mean, the real action today is in linking these different models because matter exhibit different properties at different length and time scales. And here an example of phenomena that you are familiar with. So if you witness color of molecules, you're basically seeing electronic transitions. So the interaction between light and matter at the time scale of femtoseconds. So we definitely need to describe the electronic structure to capture the behavior at this scale. But already we start looking at the diffusion of one molecule in another. So like the self-diffusion of water or ink in water, we are talking about a phenomenon that has this length scale of nanometers and nanoseconds. And if we go up into the scale, we start seeing the morphology of, for example, thin films. And here we have to characterize the formation of those films on the scale of microns. And then if we go even up into the scale, we end up at the device scale. So from millimeters to meters, and the time scale goes up to hours, but also like days and months. And then we see the propagation of cracks in metals, for instance. And so each of these phenomena require a different model. And so this is a classic example of different methods suitable for different phenomena. And as I quantum mechanics, so electronic structure calculations, classic molecular dynamics with atomic detail, coarse graining, and finite elements for the simulation of devices. So here an example of a multi-scale simulation that I have developed, and I will give you more details. So basically that's the starting point, is a molecule with all the degrees of freedom. If we remove some of them, we can basically group parts of the molecules into beads. So those colorful beads you see here, and we can get rid of the atomic structure and build this coarse-grained model of a single molecule. And with this model, we can build larger samples. And since we save on computational costs, because we have fewer particles, we can explore longer time scales. But the I would say the unique value of characteristics of this model is that the shape of the molecule reproduces the excluded volume at the coarse-grained level, and this allows to backmap the coarse-grained structure into the atomic structure, as you can see here, and carry out this addition and then a classic atomistic simulation. So this is an example of how these two levels of modeling are linked together. Right, so as I said, if we look at different scale, we need different approximations. And in the realm of classical simulations, the basis is to perform a multi-body expansion of the internal energy. Now, if you really want to know the true energy of a system, in principle, you could write an expansion such as this one, where we break down the energy of a system into the contribution of all the interacting particles. So even if we remove the electronic structure from the system, we can still break the energy down into the self-energy of the particles, their say pairwise interactions, their 3 bodies, 4 bodies interactions, and so on. But since we want to perform a numerical simulation, we have to truncate this expansion, and a classic way of writing the internal energy for an atomistic force field is to consider only those terms that have a chemical meaning. And for an atomistic force field, that would be the say potential functions describing the bonds, angles, dihedral and improper angles between groups of atoms, and finally non-bonded interactions that account for the intermolecular energy. And so here we have the Lennard-Jones potential and Coulomb potential, so the interaction between the charges. Following the same reasoning, we developed in Bologna this force field for coarse graining that is has somehow similar expressions. So a term for non-bonded interactions and a term for bonded interactions. That is basically the simulation you just saw. So this is called the MOLC model, and you see here a typical example of transformation. So that's the original molecule with 78 atoms, and we describe it with 5 ellipsoids. And as I said, the two terms are so the two terms of this sum are basically the intermolecular and the intramolecular interactions. So more in detail, we have a term for short-range interactions, and this is a Gay-Byrne potential. This is the analytical form, and it looks a bit complicated, but you can see it as a modified Lennard-Jones potential that acts between anisotropic beads, so ellipsoids or spheroids. It depends on the shape and of those particles, and but it has the familiar 12-6 terms, and we can fit these parameters to reference curves from atomistic simulations, average all of them, and get a let's say a smooth out potential that describe, like in this example, how two molecules interact in space. Then another term that not often is neglected in coarse grain force field are electrostatics, and we decided to put them in the model because we wanted to specifically study liquid crystals and organic semiconductors. So we wanted to really to capture the effect of these dipoles and multipoles that basically drive the self-organization of molecules. And the way we introduce electrostatics is by using point charges that are defined in the frame of reference of the coarse grain bead. So basically, if you see here, so in this example, we have a benzene ring, and the potential, the electrostatic potential of this molecule has been fitted with 4 charges in the positions you see here, and those are kind of attributes of the ellipsoid. So they are kind of decoration and they move rigidly with the parent particles. So there's no need to keep track of them, so to time integrate their position, because it is reconstructed from the position and orientation of the parent particle, and the value of these charges is fit to reproduce simultaneously the dipole, quadrupole, and molecular electrostatic potential. And the last term is a bonded term to keep these bits together. They can overlap in space, and so this allows to have, as I said, to reproduce better the excluded volume of the molecule. And the way this potential act is basically is broken down into a series of 16 scalar product between let's say the various axes of the two ellipsoids plus the radius describing the bond between these two ellipsoids. And then analytically we can choose to fit them with a polynomial series or with a cosine series. So that depends on the potential. And just to give you a chemical meaning, so if we take butane and we look at the potential around this central bond, we see the classic, rotation around of an sp2 carbon, and that's the profile, and the dotted lines are the reference, and the solid line is the fitted potential. So of course the scalar product is defined between -1 and 1, but it represents a full 360 rotations. Therefore, it has to be continuous at the border, and that's why this is accounted for in the fit. Right, so let's start with a simple example. So a single molecule. So in this case, we have a dopant used for organic semiconductors, is this F6 DCNNQ molecule. And you see here the shape so of the molecule if we render it with van der Waals spheres. And in this case, we use a single ellipsoid, so the shape is not perfectly reproduced. But in this case, the role of charge is really important. So we started using 6 charges to reproduce the model, and we saw the formation of these herringbone structures on the let's say on a surface, which is not really what we knew experimentally. And by using a more sophisticated model with 9 charges, we got this like slip stack configuration that is typical of strong quadrupolar interactions, and that's exactly what we have in the reference model. And this difference is also reflected in the radial distribution functions between the two between those molecules. So just to navigate this plot together, the reference would be this blue line. This is the radial distribution function from a atomistic simulation. So the solid dark line is the one obtained with the coarse grain model and 9 charges, and you see is quite in the position of the peaks quite match that of the atomistic model. While if we use 6 charges, you see the first peak is shifted at lower distances, and see the peaks are with respect to the reference, and it's a completely different morphology. And we have the proof that the 9 charges are indeed sufficient to reproduce the molecular structure, because if we then back map the coarse grain bit into the atomistic bit, and then we run a simulation with all the atoms, but from a sample that derives from this one, we basically obtain this dotted line that closely match the reference. So this method, oops, wait a second. Oh yeah, this method was used to perform a truly multi-scale simulations, where we started creating samples at the coarse grain level, then we back map them to atomistic level, and finally perform quantum mechanical calculations on the back mapped structures. And we compared those quantum mechanical calculations with reference calculations that were done at the directly with atomistic force field, just to see how good these coarse grain structures are when we run quantum mechanical calculations on top of that. And in this slide, you can see that the radial distribution functions match quite closely the atomistic reference. So there's a bit of noise in this one. So basically the interaction between the semiconductors and the dopant, that is the blue molecule, but otherwise we get a very good agreement. And most importantly, we have essentially the same radial distribution function when we back map the coarse grain sample into the the atomistic one. And here you see the side-to-side comparison between the backmap and the coarse grain samples, and see the molecules are basically this one inherits the thermal history of the coarse grain sample. We have a quite good agreement between the coarse grain and the atomistic reference atomistic simulations in terms of density, but most importantly, what we're looking here are the energetics in this system. So the first thing we computed was the density of states of the electrons and holes in the system. So we computed them quantum mechanically and then corrected them for, let's say, an infinite basis set, all that stuff, plus a term that accounts for the effects of the extended environment. So the electrostatic interactions between the hole or the electron on a molecule and the surrounding molecules. So we include the polarizability of neighbor molecules, and this interaction is accounted for classically with microelectrostatics. And what we see here is that the reference DOS from atomistic calculations closely match those from coarse grain calculations that are the thick lines. And also, we plot here the distribution of the electronic coupling, so computed between couples of molecules. And here I show the pristine samples. And you see basically there's no difference between the atomistic reference and the distributions we get from the backmap configurations. So from those samples that were created with a coarse grain model in the first place. So that's been published last month. Forgot to add the reference, but well, you can easily find, I guess. Right, now something a bit simpler from 2 years ago. I think it's a kind of evergreen because, you know, water models are, I mean, there's plenty of water models out there that are very important for biochemistry and for biomolecular simulations. So in this case, we used it to see how well to understand a bit better how this coarse grain model works, because basically for a water molecule we have exactly the same computational recipe. So in a classic, you know, rigid three body model, we have 3 particles, like 3-point masses with charges, and typically 1 Lennard-Jones potential centered on the oxygen. And in the coarse grain model, we have a single particle, which is a finite size sphere, which is described with the same Lennard-Jones potential. And there are 3 charges defined in the frame of reference of the molecule, of the sphere. And so the only difference is that in this case, we have point masses, and here we have an extended sphere. So, and it has inherently a larger inertia tensor. And also the torques are a bit different because in the atomistic model, they will act, the forces will act on the center of mass, which is slightly offset. So it's this white dot in the center of the molecule, while in the coarse grain model, the forces of, let's say, these 2 hydrogen charges act on the geometrical center of the system. So there's a slightly different torque. But besides, we can say that a system with the same configuration should have at least the same energy, and this is indeed the case. Other differences is that we can use larger time steps. So typically for a atomistic molecular dynamics simulation, you would use 1 or 2 femtoseconds maximum, and we show here that we have very good properties with a 10 femtosecond time step, which is a huge bonus, because basically means we can run simulations faster just by increasing the speed of time integration. And here a comparison of what we get. So basically, when we compute the viscosity and we compare the atomic reference versus the coarse grain reference, we see that the coarse grain model has a slightly higher viscosity. We also studied 3 different water models and 3 different system size. So we don't see a strong correlation with the size of the system, and the 3 models are well separated. So the differences are really down to the models used. And in the other panel, we see the self-diffusion coefficient, and as you can see, that it's computed on the mean square displacement, and is basically complementary. So if we have a slightly higher coarse grain viscosity, conversely, we have a slightly lower self-diffusion coefficient, but that's entirely within the range of the experimental value of water. So I would say that that's quite a good result. Then we compare the radial distribution functions, and in this case, they match exactly that of the reference model. And for the coarse grain, we backmapped the position of hydrogen atoms, but we did not relax the system further. So this is exactly, I mean, this let's say extrapolated hydrogen and hydrogen distances from the coarse grain simulations are really is information that is included in the coarse grain model. And finally, so we wanted to test how so what was the effect of the time step on various properties. And basically a common trick in molecular dynamic simulations is to use fictitious masses or masses with I mean, increase the mass of a particle to slow it down and use a larger time step. And this is a reasonable approximation if you want to model stuff that has different sizes, and therefore you don't want to slow down the simulation because you have lighter particles. So in this case, we wanted to see how much the so this increase in mass decreased the properties, or like affected the properties. And in terms of density, if we scale back to the nominal density, we see no effect. Also, the radial distribution functions are not affected. So the statical properties are not affected by the use of larger masses for water or longer time steps. But what is indeed affected is the viscosity. So, and that's totally expected. So if we use a mass too big, we basically end up with a viscous liquid that does not resemble water at all. But let's see, the interesting result is that with 15 femtoseconds and also with 20 femtoseconds, there's just a small increase in the viscosity. So it means that so if we stick to this range of time steps, we still have a decent model of water for, let's say, simulations where we really want to push on the performance. Oh, again, some stuff not shown here. Another example is this polymer PLGA. So that's another application of this coarse grain model, and we computed the glass transition temperature and see that it is affected by the morphology. So we can see that basically the same number of particles and in the system, but with different morphologies, result in different glass transition temperatures, and this bar is the experimental range. And this is, I guess, a very nice result because it somehow it has an industrial value because it correlates the thermal history of or like the procedure with which a polymer is produced and then you know prepared experimentally, and this affects the properties of the material. we also computed the thermal conductivity, and I mean it's good in terms it matches quite closely that of the reference calculations, except that we do not see a big difference between the two morphologies, while we see this difference in the atomistic models, and probably that's due of the poor statistics, because let's say by having the same system size, we have with the cross-grain particles, we have less particles in the binning, in which we like partition this sample. So probably we need to study larger samples to really test this hypothesis. Also, we computed elastic constants from stress strain curves. So we deformed elastically the cell of these polymers and compute the various moduli. And you can see, like, again, a quite good agreement between the reference atomistic calculations and the cross-grain results in green. And to conclude the section on science, is the last example is a large surface of P3HT, which is a conductive polymer. And so the unit cell in this rendering was 22 per times 30 nanometers, so quite large one. And in this example, we were studying the interface with the MSO. But interestingly, if we look at the morphology of this planar configuration, there is apparently a way to produce this surface experimentally, and this is a one-to-one comparison between a AFM image showing that particular crystal surface and the corresponding model. And so if you count, that's the same number of stripes, and they are exactly in the same scale. So quite nice proof that with good cross-graining, you can indeed access a number of interesting properties. So that's basically what I've been doing in academia. And this is a kind of description of what happened next. So up to 2019, I was doing this stuff in Bologna. And it was done with this XMOS project. And then I received funding by two entities, Fondazione Golinelli in Bologna and University of Bristol, UK. And I entered in these two incubators, a reactor in Italy and QTech in Bristol, where I received training and started to engage with the industry. So and the idea was, can I bring advanced molecular modeling techniques to industry? And that's what I've been doing in 2020 up to 2022. And I have to say, a lot of sleepless nights and a lot of learning. And eventually I landed in Goldbeck Consulting, and that's where I'm working right now. Well, what I learned is that, as I said when we were chatting at the beginning, there's a translation problem in industry. So people know how to, fine-tune their machinery, how to, create a new formulation, how to test it, but the kind of expertise required to use those advanced molecular modeling techniques is often lacking, especially in small companies. And most importantly, different communities often use different notations, different language, and that's a big problem. Because if we do not understand each other, basically we keep working in isolated compartments. So one of the solutions we are exploring to fill that gap is to use ontologies. So a formal description of knowledge. And this is a technology that's that has been developed originally for web, to add semantics to text in the web. And one of the things you're certainly familiar are like recommendation systems, where you can infer connections between concepts, and then therefore suggest relevant content to users. I hear some beeps. I don't know if I stop or I'm over time.
It's okay. We can join in the room.
Okay, perfect. Yeah, other ingredients for this translation are FAIR data, where FAIR stands for findable, accessible, interoperable, and reusable, and use of open simulation platforms. So something that is open source and people can inspect the code and can transparently make amendments and discuss new methods. And also like use standardized workflows. So the more complex a computational workflow, the more we need to document what's done, how it is done, what it does, because if the expert leaves, then no one knows how to use it anymore. So what we tackle specifically in this open model project is this problem that I try to represent here. So with computer simulations, we try to replace, the person working in the lab with a person doing the same work with a computer model, we have exactly the same problems. Is that the work depends on the person, no one is sure how it is done, and documentation is often lacking. So what this project is doing is to create a modeling platform that is open access and open source, and is created for industry. So in the project, there are a number of industrial partners that are sharing their industrial problems, so what they do in the lab, and there are a team of translators that are using their expertise in academia to create workflows specifically for this problem, for that problem. But on top of that, we describe these workflows semantically with ontologies, and everything is can run on a standardized platform that has this kind of architecture where the ontological description is used to query the database to retrieve information on workflows. This information is then translated into a specification that is then executed. So since it's machine readable, we can then translate this knowledge directly into a workflow that is executed by a workflow manager. And finally, we can use the data that have a description, so that we know what, let's say, the conventions of a specific program, so we can describe how what are the units of measure of the numbers we get, where those data are stored, how a certain property was computed, which protocol was used, was it validated, does it agree with experimental data. So all of that can be assessed automatically because it's created in this semantic database. And so the ultimate goal is to foster innovation. So those are some of the challenges in industry. So I mentioned that lack of documentation, but also a very steep learning curve for people that really don't have a PhD or a postdoc in computational chemistry or similar, I don't know, fields. Then a problem that I experienced firsthand with one of those work I started early in the talk is that when you really want to do coupling multi-scale simulations, you really have to create the glue between different models and different programs and convert formats, units, and keep track of all of that. And it's a lot of work. And then once you have it, you have still to execute all those simulations, do sanity checks, like if you are studying a library of compounds and you don't do that with the workflow executor, and there's always a risk that you make mistakes and typos, and that will affect the results in unforeseen ways. And finally, you are left with the task of data analysis, and all of that can be tackled. And the proposed solution would be to use specific translation tools and define materials relations. So it's we're not reinventing the wheel. We are using standard vocabularies to describe what we do. And part of this is also the semantic description of models and data, so that we can retrieve those models with queries that are human readable. So we can say, oh, give me a method that is suitable to compute this observable, and then we can infer what is the best model for that task if the knowledge is present in the database. Then when we create new workflows, we can document them, and so we can retrieve and understand what they do, and at the same time we can execute them with a workflow orchestrator. And finally, everything is automated, and new data being produced will be stored automatically in the database and can be accessed through queries. And so that basically it's a modern way to enable digital high throughput material discoveries. Basically, we set the parameter space and we let the machine do the calculations. And of course, if we have a lot of data these days, how not to cite the possibility of doing good machine learning with this data. And then the plus would be that those data are based on validated physics models. Right. So almost finishing here. So my role at the moment is that of a product manager. So in this project, I am making sure that what we are developing meets the needs of the end user. And my use case that I'm describing in this platform is another toy model that basically uses the stuff you saw I've done as a postdoc in research. So water and PLGA polymer to create a water permeable membrane, and this is a truly multi-scale simulation where we first assembled and equilibrate the system at the coarse grain level, and finally perform the atomistic simulation and study the diffusivity of water in this membrane. Right, so that brings me to the conclusion. So on the science side, I've described this MOLC model that is a coarse grain force field that I've contributed developing in Bologna, and is based on spheroids. And the force field is based on short and long range interactions plus directional bonds, because those ellipsoids overlap in space. And the consequence of this choice is that the shape of the molecule, the coarse grain molecule, approximates very well the excluded volume of the original model. Therefore, we can have a seamless conversion between coarse grain and atomic coordinates. That multi-scale workflows are needed if we want to describe phenomena at different scales, and we need to couple them in some ways. All of that, so all the work I've done was done with open source software. So the MOLC model is available in labs. and the force field is rendered with this molten plate program. And that's the website of the company I funded to maintain like the software. So basically all the new articles that are being published since the end of my work in academia now are published under this umbrella. And finally, to make all this work available to industry, I'm working in this open model project that basically will provide this platform that supports modeling workflow building, management, documentation, execution, and tracking, and all of that using semantic technologies. Well, I need to acknowledge you for funding, you for your kind attention, and my colleagues that help me with the coding and stuff. And thank you so much for your time. So I think we have time for questions now.
For a wonderful talk. Really appreciate it that you are here talking with our students who are computational material researchers, and you are giving your perspective from both sides. So, and as you said, there is a language barrier, and there are very few people who understand sport. So thanks a lot, Otello, for that. And yes, the floor is open for questions.
Yeah. There's a way out of academia. If you wonder.
Yeah. Questions? All right. So I have the force field model. I see there are a lot of polymers that all the examples were related to polymers. And do we are there force field developed for inorganic materials or solids that are easily available that we can use? And that's my first question.
Right.
And
yeah. Okay, go on, and then I'll answer both of them.
Is that I feel like is it applicable for crystalline systems? In the last, I think, example we saw that the material was pretty crystalline, or if I can imagine, it would be useful more for amorphous materials or disordered systems rather. So could you please give us some advice where these force fields can be used in inorganic world, inorganic chemistry?
Right. Yeah, that's a very specific question, and I would say for inorganic. As you see, the idea behind cross graining is to create beads that are as big as possible, and it works very well with organic compounds because, of course, there are. I mean, for condensate systems, it's pretty obvious that you can replace, a large ring or poly rings with kind of flat disc-shaped or elongated bead. But for inorganic crystals, it's a bit trickier because let's say you have large differences in mass and let's see, between the metal ion and the counter ions, and therefore it's a bit less obvious how you partition the system into like how you create the repeating unit. But I mean, it can be done in principle. I mean, there's no I would say the only problem would be to manage the connectivity, because you have to define vector. So the bond is not only between neighbors, but you also have to assign a direction. So so it would require a bit of extra programming when you create the sample. I haven't done it yet, But something I've done was to study, to test this coarse-grained model for organic crystals. And maybe I have a slide. Let me check somewhere else. And I would say it works pretty well in the sense that, let's say for let's see, saxitiphin, I basically I can reproduce the triclinic structure. Of course, it's not as the atomistic reference or the experimental one is, but the error is, I would say, the volume, the error on the volume and the density is within 5%, which is quite good, but the angles are slightly different. I would say maybe 10 degrees difference. Now I don't remember exactly the numbers. And also I tried a fatty lipid, maybe the or I don't know, something similar, and of course P3HD. I've tried a small supercell with perhaps 4 repeating units. So I mean the take-home message there is that even though you would not expect say good precision from a coarse-grained model, for certain molecules it performs quite well. So yes, it is possible to do to model crystal structures. I guess something I would like to do in the future would be to model one of those molecules or polymers with long aliphatic chains as side groups that are used to enhance the solubility and processability of the system, but from the modeling side, they add a lot of complications. So if you model them with full atomic resolution, there's a lot of minima and ways they can tangle with each other, and that's very little chance that you will sample efficiently the configurational space. And I think, yeah, coarse graining could be useful to like explore, like say the morphology of those crystals.
Thank you so much for explaining this, and I understand that this is still a developing field. There's a lot to do, and specifically, I would imagine that for disordered systems, we can still have a unit. For example, if we have silica, we can do SiO2, and then we can put together all of them to create a disordered system, which is sometimes done, but then I understand with other systems it would be really hard to do, especially in inorganic world. So another small question that I have is the workflows that you mentioned. So some of us work with a lot of data, and we design our models, and then we create our scripts, and then we use a supercomputer to run those simulations, collect the data, analyze the data. So this whole process using these workflows, are there any restrictions that these workflows can be used only for certain type of simulations, or they are built, they can be useful for all the possible scales of the materials, different types of materials, different softwares? So please tell us something a little bit more about these workflows, because I think many of us can get benefited from those workflows for sure.
Yeah, yeah, indeed. So specifically for this project, we are using AIDA as workflow manager. I mean, there are several choices, and there was a review paper from the people in Battery 2030, sort of like reviewing different workflow managers. So by no means AIDA is the only choice, but this is the one we are using in OpenModel. And I mean, AIDA is developed by the group of Nicola Mazzaria, EPFL, and it was mainly developed with electronic calculations in mind. So you find already a lot of wrappers and examples for codes like Quantum Espresso, Siesta, VASP, and the likes. And here, what we are doing is also facilitate the use of all the software in a way that does not require writing a specific plugin for AIDA. So it's in a way, and they use the shell to access the command and only document semantically the information that the program needs to run the simulation, like something at the implementation level, like the various flags or command line options that are needed, but also at the simulation level. Let's say if we want to, if you want to capture, I don't know, a specific thermodynamic ensemble and like a macro that defines it, or let's say we want to connect an observable with one or more protocols to compute them. So all of that can be described in the ontology, and then the application. So the implementation is linked to that description, and everything can be assembled on the fly. So the added value of the platform would be to make complex queries, or like even to ask for a property for which there's not a simple workflow available, because you have to combine different stuff together. But if the system has the knowledge that in order to get that observable, I need those ingredients, and in order to get those ingredients, I need, I don't know, 1, 2, 3 different workflows to predict them, then so if every, say, task was documented with the input and output specified, then the ambition here is to make a query that works its way back from what you want to what you need to do, and then extract this information, render it in a way that it can be machine executed, and then you get your workflow assembled on the fly and ready for execution.
That's amazing. Thank you so much.
I mean, but someone has to first describe all the stuff in the workflow. So we are providing a few examples, and let's say we are initiating the knowledge base with a number of different software, like I mentioned lamps, but there's also Fluent, I don't know, stuff for with I don't know, it's called lights for finite elements, and I mean other codes as well. So basically, the idea is to show how to implement different models in the system, and provide examples so that people can use it or just, you know, query what's already there and see if it's of any use.
Yeah, I think that would be really useful for high throughput calculations and all the data scientists. And currently, in one of our projects, we are doing about 70, well, not a lot compared to many other groups, but about 10,000 calculations for 75 different materials. And so even managing that is a big task. So if you do it manually, so some parts of it we can automate, for some part of it we cannot, for some reasons. We're not able to, you know, we're not able to work with our supercomputers here to seamlessly just run all those simulations in one go. So these kind of workflows could be really useful in that case if we can try. So I think it's a really good initiative from your side to provide that, for sure.
Keep an eye on open model then.
Yeah. Any other questions?
I have a question.
Yes.
Yep.
Thank you for your presentation. You mentioned that after your postdoc in Bologna, you joined an incubator, I think you mentioned. Can you explain a bit more about how did you end up going there, and if it's like a transition, like a necessary step to transition into industry, or what was the reason?
Well, I would say it's a bit of serendipity. So like something happened at the right moment, but I was ready to listen. I mean, I have to say that certainly personal motivation was a main drive. So the idea that this work I've done in Bologna was producing good results. I mean, good scientific results, and I still keep publishing like a couple of papers a year on this, and still keep developing the model. But since like it performs quite well in terms of structural and dynamical properties, I thought that maybe it was a bit of a waste to use it just, to increase my H factor. So the idea was, why don't I try to engage with industry and see if it can solve some real problems, let's say for energy production, or to design better materials. And that's where I've learned that basically there are commercial software to do so. Certainly, I mean, I was aware of Schrödinger or Piovia, specifically for materials modeling, but still, we still don't see this, let's say, this huge change in the way we produce, use, and dispose of materials. So it's pretty much dominated by plastics, and I mean, except for like aerospace applications, there's been more going on in that area, but the rest is pretty much so there's not let's say a radically new alternative to producing certain materials that say is displacing the way we, let's say, use wheat or like metals, and so that was the motivation. And I've been lucky that there was this program running in Bologna, and and I got an email from the foundation, so from this institution in that was spamming all the postdocs, apparently looking for ideas in the deep tech space, so coming from research. And that was the first accelerator. And then when I entered, I really knew nothing about like how to let alone how to create a company from scratch. So it was like very confusing. But eventually, that landed me in Bristol, and so that was a bit longer program, 1.5 years. So there was more time digest those new notions and try to do it. So to be honest, my mates are doing way better than I do. So like they're following the proper startup narrative of funding and selling equity, and growing and developing their IP, while in my case, I'm working with open source software, so I'm not really trying to sell it. I'm really trying to make the industry use those tools. So the end goal is not to have more computational chemists in industry, is to have the computational chemistry as a tool be used to make to make the process of materials discovery faster, more efficient, and potentially to access new materials that would have required a too laborious work to or like people didn't think of, because they weren't sure if they would work. So yeah, that's the idea.
That's awesome. So the take-home message for the students, if they want to go into industry, is that read your emails, because you got an email, probably they will get one too, where they will have the platform to start their new venture. And I understand it's a big jump going from academia to industry, so nobody knows when they enter, but there's a learning process. Everybody has to go through, so which is
Yes,
it has to be.
but don't worry, it's not worse than 10 years of postdoc and public funding. So if you've done it, I think it's downhill.
Perfect. If there are no more questions, I would like to thank you again, Otello. It was wonderful having you here. Hopefully sometime we can have you in person. I don't know if Wadok is happening again here, but there are many conferences that are happening again. So it would be very nice to see you here, and really appreciate your time.
Thank you for the invitation.
Thank you.
So much. Just thank our speaker once again. And of course, I
Thank you,
would like
Betsy.
Emmanuel as well, because without Emmanuel, I wouldn't have had the opportunity to hear this talk. So thank you.
Well,
Emmanuel.